Let me start the presentation now. Hi everyone. First of all, I really appreciate for watching this session. My name is Lee Byuk-san, and I'm working at LINT as a software engineer in API Gateway team. Today, I'm going to talk about connectivity improvement between LINT client and server with HTTP2 and TLS. This is the agenda for today's presentation. I will start off with some background on what we try to solve, and then I'll explain three main approaches we took to improving our connectivity. At last, I will finish this presentation with a summary. First, background. Before getting into the details, let me clarify the scope of this presentation. This diagram describes the overall structure of LINT messaging platform. LINT clients communicate with talk server and collaborative services either directly or indirectly through API gateway, which we call LEGY. LEGY is short for LINT Event Gateway. From here, I will use terms LEGY and API gateway interchangeably. Talk server and collaborative services run their own business logic to provide LINT's features such as messaging, media transmission, and so on. One of the LEGY's main responsibilities is to manage connections with LINT clients. This presentation focuses on the communication between LINT clients and LEGY. Because most traffic to LINT services come through LEGY, LEGY must be able to handle the connections in an efficient and reliable manner. Also, it must be secure. So let's see how the protocol between LINT clients and API gateway has been changed. When LINT began as a service in 2011, we used HTTP 1.1. As you already know well, HTTP 1.1 basically uses one connection for a pair of a request and a response. One of the main functionalities of LINT was to inform the clients of new message arrival over HTTP 1.1. For that purpose, we've used long polling technique. This is how it works. Every event in LINT is defined as an operation. Clients synchronize the events using an API called fetchUps, which returns the operations. LEGY handles fetchUps request as long polling. LEGY passes the fetchUps request along to talk server right after receiving it from a client. But when talk server responds no content, LEGY waits for a publish from talk server. When a new operation is created, talk server sends a publish request to LEGY. After getting the publish from talk server, LEGY resends the original fetchUps request to talk server and sends the response back to the client. Since the end of 2012, LEGY has started to use SPDY, which is the basis of HTTP2. Unlike HTTP 1.1, SPDY establishes one TCP connection and multiple requests and responses are multiplexed within a connection. Besides this, SPDY has more improvements over HTTP 1.1. The first one is header compression. SPDY reduces the size of HTTP headers by compressing them because a request might carry big headers. This was good for reducing network bandwidth, but it led to high memory usage for LEGY for storing compression states. In such a situation, LEGY couldn't support header compression correctly for some connections. Because many requests from a client are likely to have same HTTP headers repeatedly, and we know what they are, we decided to cache such repetitive headers in LEGY to reduce both network bandwidth and memory usage. Within a connection, when LEGY receives a request, it holds cacheable headers in its memory and returns a cache key to the client. For a later request, client can just attach the cache key as a HTTP header, then LEGY restores the cached header before sending the request to the backend server. The second improvement from SPDY is server push. Server push enables multiple responses for a single request. Its purpose is to make getting additional resources to render a web page faster. However, even though it is called server push, it requires one request. Some line services need subscribe and push pattern to avoid empty no content response when using long polling. It requires unsolicited push, which requires no request for a push. To enable such push method, we associated every push stream with stream 0 because stream 0 is not used in SPDY. This is totally invalid according to the SPDY specification. In our push mechanism, client first sends subscribe request to a service through LEGY. After that, the service sends push request to LEGY, then LEGY finds the associated client's connection. It sends the data in a stream, associating it with stream 0. Note that FetchUp's API does not follow this pattern and it still works as long polling. Security is a very important part in communication. For SPDY, it is recommended to use TLS for the better security, but at that time, it was a very big overhead to use it because it slows down the connection establishment in 3G mobile network. Mobile network was too slow and disconnection and reconnection occurred frequently. So, we made in-house encryption method called LEGY encryption. LEGY encryption encrypts only the message body and some sensitive headers, not the whole connection. The handshake process is similar to zero-RTT handshake in TLS version 1.3. The encryption key exchange and HTTP request and response are processed at the same time. When using LEGY encryption, some metadata about LEGY encryption is added to headers. Every sensitive header in request and response is moved to the message body, and they are encrypted with the original body. Clients connecting a Wi-Fi network usually uses TLS, but others in mobile network use LEGY encryption. I introduced some techniques we've used so far to improve the connectivity between line client and LEGY, but there are problems. First, SPDY itself is deprecated and there's no library to work with our SPDY protocol. We should write and manage our own SPDY code. The second problem is that our protocol is not standard conformant. It's confusing and makes network debugging hard. The last problem is that TLS is better and safer than our in-house encryption method, but we don't use it for all connections. Our mission is to make line more reliable and more secure without harming user experience. LINT, short for Line Improvement for the Next 10 Years, is a project to improve the blind spots we overlooked during rapid growth and to prepare the next 10 years for line services. As one of the epics of LINT project, we try to solve the problems I described earlier. The goals of these projects are to replace all the SPDY protocol with HTTP2, to use standard conformant push mechanism, and to adopt TLS for every connection regardless of the client's network environment. From now, I'm going to explain what we considered and what has been done. Using HTTP2 is simple. We can just replace SPDY protocol to HTTP2. Note that we use standard HTTP2 and header cache is not used anymore because it is replaced by HPAC, which is an efficient header compression method used in HTTP2. I will focus on how we safely switched over to HTTP2 rather than describing HTTP2 compared to SPDY. There are two bad cases which make the migration unsuccessful. The first bad case is that server implementation has bugs. Unlike clients, we can always fix the servers, but what matters is how long it will take to fix. If a bug is non-trivial and takes a long time to be fixed, the best way to handle it is to disable HTTP2 entirely until the bugs are fixed. This requires the ability to control client not to use HTTP2. The second case is that client-side HTTP2 is buggy. In this case, the client may fail to send requests or get response. The failure can happen temporarily or permanently. In the worst-case scenario, requests for all line services will fail. In order to deal with such a situation, the client must be able to use SPDY, not only HTTP2. This diagram describes how the communication works. Instead of using the protocol directly, Network Abstraction Layer has been introduced to manage the protocols. It determines which protocol to use and handles any protocol level problems. The default protocol would be HTTP2. This abstraction layer is useful not only for HTTP2 migration, but also for the future protocol updates. When something wrong happens, the abstraction layer detects it and switches to SPDY. Thus, the client can use line services without any problem like the previous version. When we need to disable HTTP2 for all clients, we update the external configuration. The updated configurations are propagated to client's network abstraction layer. Then, the abstraction layer excludes HTTP2 from the usable protocol list, and the client uses only SPDY. Of course, if we turn on HTTP2 in the configuration, Network Abstraction Layer starts to use HTTP2 again. To configure the clients, we use connection info or CONINFO. Connection info is a network configuration defined in LEGY. Clients fetch it to determine their network behavior. It defines where to connect, how to connect, and some feature parameters. This is not a new thing. We've defined and used CONINFO for a very long time, even before HTTP2 is considered as the next main protocol. Why do we need this? It's for reliability. As a global service, we have several LEGY POPs around the world, and LINE is being used in various countries. Clients should be able to connect to the appropriate POPs for fast and stable communication. Different countries have different network characteristics, so we cannot just apply the same network policy for all countries. Each client type can have its own network configuration to optimize the performance on the platform that it runs on. And the service features are added and removed as the applications are updated. So we control the configuration basically depending on the user country, client type, and client version. The main usage example is New Year preparation. Because we know that right after it becomes New Year, the traffic burst occurs, we configure CONINFO to disable or reduce automatic request retries. Here is an example of CONINFO. The top-level key, LEGY here, indicates the configuration item. This example configures LEGY server item. The keys at the next level are countries. This example has two, all and JP. All works like fallback configuration. If a client is not suitable for JP configuration, which is used for Japanese users, clients use configuration under all. At the next level, client types and versions are specified. This example defines different configurations depending on client versions. Android client under version A.B.C and iPhone client under version X.Y.Z will use the first configuration, and the others use the second one. Other client types are not configured, so they cannot use this configuration. Note that in real configuration, we configure for all client types and versions because every client must be able to connect to LEGY. The configuration is divided into two groups, mobile and Wi-Fi. This specifies which configuration items should be used based on the client's current network environment. Each has a list of LEGY server information with priority. Client's network abstraction layer refers to this and selects appropriate protocol to be used. Secure field specifies whether to use LEGY encryption or TLS. Android and iPhone clients after specific versions are configured to use HTTP2 as the primary protocol. We can disable HTTP2 entirely by replacing this field to SPDY. There are some cases where clients cannot use LEGY's CONINFO. One example is when the client application is newly installed on a user's device. For such cases, LEGY must share default CONINFO with clients so that clients can work even when they have no CONINFO data retrieved from LEGY. Default CONINFO is extracted from LEGY's configuration to a separate repository. Clients import this repository into their source code, and the configuration is shipped within an application binary. When the client runs, it first checks if it has local cache for CONINFO. If not, it consults with the default CONINFO to decide LEGY servers to connect to and fetches the latest CONINFO. If it is successful, it caches the fetched CONINFO data into their local storage and uses it to determine its network behavior. If it fails, it uses the embedded default CONINFO. CONINFO is used as the main tool for safe migration from SPDY to HTTP2. This is our step-by-step migration process. For all steps, connection info configures HTTP2 as the highest priority protocol with SPDY as fallback protocol. After beta and RC test, we released HTTP2 into production, but with a restriction. Unlike in beta and RC, clients are additionally configured to restrict users who can use HTTP2 in production. We allowed HTTP2 for line employees first, and then line users in Japan, and then finally the globe. The HTTP2 entries in connection info were ignored by the client if the user is prohibited to use HTTP2. Fortunately, there were no big problems during the migration process, so connection info was never updated to disable HTTP2 globally. Currently, 85% of the connections to LEGY are using HTTP2. We are going to prepare the complete removal of SPDY code in the client soon. Now, let's move on to the next topic, streaming push. Let's recall the requirements for our server push. It should follow the HTTP2 standard and should be easy to use. Additionally, the unsolicited push must be available. Like SPDY, HTTP2 also offers server push, but in a different form. HTTP2 defines push promise frame, which plays the role of pseudo request. Before sending a push, a server must send push promise to the client to let it know that there's something to be pushed. Each push is transmitted in separate streams from the stream where push promise was sent. In this diagram, two push promise frames promise that two push data will be sent in stream B and C. Using this feature, we first came up with the sequence to make unsolicited push available. The only difference from SPDY push is that LEGY sends push promise in every stream related to push. Push promise is sent with the subscription response, and each push also sends push promise for the next push. However, the HTTP2 standard says that push promise must be used in the client request stream. Even though this push model worked when we tested with browsers and some libraries, it seems to be not standard conformant, which is one of our server push requirements. Besides standard conformity, there's one more thing we should consider. Suppose line clients use the previous push model, but the connections are managed by a library or the operating system. To get pushes, line client first sends subscribe request and it succeeds. Now, the client believes that LEGY will send push data when it needs to. However, because the client does not have controllability on the connections, it can happen that the library or the OS closes the connection within which the subscribe request was sent. From LEGY's point of view, client is disconnected and then subscription is invalidated. So, LEGY will not send any push to the client. The client does not know this situation and it still believes that the subscription is alive. This is a problem. This does not happen with SPDY protocol because line clients implemented SPDY protocol itself and fully controls the connections. But with HTTP libraries, we cannot guarantee that line client can fully control the connections to prevent such problem. We know that the clients can control HTTP2 streams regardless of the library it uses. Clients can determine when to start, pause, and finish a request. Thus, it is natural to create push session within a stream, not a connection. Then, for LEGY to push, a stream should not be terminated unless the session itself is finished. This is exactly what chunk transfer is for in HTTP 1.1. It enables data streaming. LEGY can respond to a subscribe request with chunk transfer and send data when prepared. We can do the same thing in HTTP2 with no harm in a single connection because HTTP2 connection is multiplexed by multiple streams unlike HTTP 1.1. In HTTP2, the message body is divided into multiple data frames. HTTP2's data frame intrinsically works as chunk transfer in HTTP 1.1, which means HTTP2 naturally supports data streaming. We use this streaming nature of HTTP2 to send push, and we call this streaming push. Does it satisfy our requirements? Yes. We didn't change anything with HTTP2, so it's standard conformant. This makes using any library for streaming push easy. Lastly, we can send unsolicited push to the client. This is how it works. A client opens a stream to a specific path, then both client and server know that this stream is used for streaming push. LEGY responds 200 right after it receives headers, and push session gets open. The actual subscribe requests are sent as sign-on data within this session. LEGY subscribes necessary services and returns subscription result to the client. Whenever service sends LEGY push data, LEGY sends unsolicited push to the client. Based on the push type, client may send an acknowledgement for a push back to client. Long polling requests can be handled as well within a streaming push. Unlike subscription, where sign-on data is sent only once at the beginning of the session, long polling repeatedly sends sign-on every time the client receives the sign-on result. Thus, fetch jobs can work within a streaming push session or a separate stream. The last topic is TLS. I said that we use TLS, an in-house encryption method, at the same time to improve the speed on mobile network. Let's briefly see why TLS Handshake is slow first. We are using TCP as transport regardless of the upper-level protocol. When using plain TCP, the sequence of communication is very simple. Client and server perform TCP three-way handshake, which makes one RTT, and application data starts to be transmitted right away. LEGY encryption runs on plain TCP. The right diagram shows how TLS version 1.2 works. Because TLS works on top of TCP, three-way handshake is performed as well. Before the application data is transmitted, TLS handshake must be performed to negotiate cryptographic parameters used in the TLS session. The negotiation consumes 2 additional RTTs, which is critical in slow network. Also, disconnection and reconnection are very frequent in mobile environment. This makes the situation worse. Fortunately, TLS version 1.3 basically supports a better handshake mechanism and reduces the negotiation to 1 RTT. With some settings, TLS version 1.3 provides 0 RTT handshake so that application data can be sent during the negotiation. Adopting TLS version 1.3 as server seems resolve our concern about deprecating LEGY encryption. However, using TLS version 1.3 is not enough because many clients are still using TLS 1.2. Can we make the negotiation 1 RTT in TLS version 1.2? When connecting to the server, clients does a 2 RTT handshake to negotiate the cryptographic parameters. What if we reuse the cryptographic parameters used in the first connection when connecting to the server again? We can reduce handshake if client and server can remember the session information such as cryptographic parameters and agree to use it. It is called session resumption. There are 2 techniques for session resumption. One is session ID, which TLS 1.2 supports, and the other is session ticket, which works as a TLS extension. Session ID is to store the cryptographic parameters in the server. Each stored session is given an ID. In this example, a session is newly established and the session is stored with ID 1 in the connected LEGY server. When the client tries to reconnect to LEGY with TLS session ID 1, it's likely that the client connects to another LEGY server instance. Because this server does not know about the session ID 1, full TLS handshake is performed, which consumes 2 RTTs without any improvement. For session ID to work, all LEGY instances must share their session storage. For session storage, we use a Redis cluster. Each session is stored across the Redis instances using rundev hashing. LEGY now knows which Redis instance to ask for a given session ID. In this example, LEGY server, which takes the second connection, now successfully restores the session information and finishes the handshake in 1 RTT. As you can see, session ID is a stateful technique, so we should store all sessions consuming our resources. To reduce our resource usage, we also used the other technique, session ticket. Unlike session ID, session ticket is a stateless session resumption. Instead of storing the session in the server, LEGY creates a session data called ticket and returns it to the client. A session contains the session information so that LEGY can obtain session information, extracting it from a ticket. The client associates the session information it uses with the returned ticket. A ticket is encrypted using LEGY's secret key, so clients cannot manipulate it. For security purpose, LEGY rotates encryption keys, and LEGY keeps a window of keys so that old ticket can be used for some time. The keys for the future are provisioned to prevent absence of key. This makes the key synchronization across LEGY instances much easier. For session storage, we use When client connects to LEGY the second time, it sends its ticket to LEGY. LEGY decrypts it and validates it. If it is successful, LEGY uses session information extracted from the ticket, and client uses session information associated with the ticket. If the ticket is expired, full TLS handshake is performed. The only thing we should consider from the server side is key management. We distribute the keys using our key management service. Keys are generated by LEGY. Because all LEGY instances run the same logic, our cron job sends a future key generation request to one of LEGY instances. The generated keys are uploaded into key management system. LEGY instances periodically discard old keys and fetch the future keys from the key management service and fill up the window. This ensures that all LEGY instances use identical keys for ticket resumption. This is the result of our TLS improvement. The packets are captured during TLS connection establishment from client in Korea to LEGY in the United States. The first TLS 1.2 connection consumes 2 RTTs for its handshake. It took 600 milliseconds. The below 2 images show that using session ID and session ticket reduced the handshake to 1 RTT, which took 300 milliseconds, half of 600. TLS 1.3 always performs handshake with 1 RTT. You can see that no matter that it uses session resumption or not, handshake is done in 1 RTT. Currently, we use TLS for the recent clients and we will use for the future clients in both mobile and Wi-Fi networks. As a result, 93% of all connections to LEGY use TLS. 80% of them use TLS 1.3, and 20% of TLS 1.2 connections are using session resumption. As time goes on, and old clients are upgraded, we expect that the TLS usage and portion of TLS version 1.3 will increase. Now, let me summarize today's presentation. It's been 10 years since LINT was created and it became a global service. LINT will be growing for the next 10 years as well. For that, we believe that we should improve our reliability, extensibility, security, and various aspects without harming user experience. As the first step of this goal, we tried to improve our network stack. For security, we adopt TLS more aggressively. But to reduce bad impact on users, we also adopted TLS version 1.3 and implemented session resumption techniques, session ID, and session ticket for TLS version 1.2. As a result, 93% of connections are using TLS. For reliability, we started to deprecate old and customized SPDY protocol and satisfy the standard by adopting HTTP2. 85% of connections are using HTTP2, and as time goes by, all clients are going to use HTTP2 and SPDY will become obsolete. For extensibility, we implemented a push mechanism named streaming push without customizing the standard. Long polling and subscribe requests can be processed as we want. With this mechanism, we can seamlessly migrate long polling requests to actual push in the future. Global network environment keeps changing and new protocols keep coming out. IPv6 begins to be widely used. New protocols such as HTTP3 and QUIC are discussed. Maybe new version of TLS will be out. Some encryption method can be found to be vulnerable as computing power gets more powerful. There are various factors in network. We know that reliability, stability, and security are the keys to quality service, and we are going to keep enhancing our connectivity against the ever-changing network environment. This is the end of what I prepared for today's presentation, and I hope you enjoyed it. Thank you.